Hello and welcome to the Acadec tutorial video for Focus Quizzes 21 through 23. Properties of similar figures, area of a circle, and angle measures in a circle. Now, that first one is deceptively easy in my opinion. That second one is just easy in my opinion. And that third one takes a little getting used to, but then once you are used to it, I also think it's easy. Now, all of these are really important for you to know and to know them well, because these will be the types of questions on competition exams that they might add twists to, or they won't, and it's easy points. But if you mess it up and can't get it, that's very unfortunate, because if they are the easy points and you don't know how to do it, it means the other questions are going to be harder by comparison because they thought that was the gimme. So figure these out is my advice to you. All right. Okay, so similar figures are just shapes that are the same in every way except size. So all the angles are the same and all the proportions are the same. So if you split, and this is from the resource, and I don't even know if it says it in the resource, but these endpoints bisect these two side lengths. So this triangle is similar because all of the proportions and angles are the same to the whole triangle, not that little trapezoid down there, but to the whole triangle. And that is decently often how similar figures will be presented to you, as a proportion of a larger object. So the smaller one will be. This is that same triangle, but we've further split it into 4 equal triangles, and I'm going to use this, the resource is going to use this, to teach you exactly how the different proportions work. So this endpoint, and this endpoint, and this endpoint all bisect, so they split perfectly in half their respective sides. And that means that this side length of this smaller triangle is what we're going to focus on right now. This side length is exactly half as long as the whole side length here. We call that a full 1. And that means that the proportion of this side length to this one is, or rather this one to this one, because we want whole numbers, is 2 to 1, or 1 to 2, depending on which one you want to put first. But the larger one is scaled up by a factor of 2 compared to the smaller one. And that holds true for the whole perimeter as well. So we don't know these side lengths, but if we did, we would see that when we add up the whole perimeter, even though it might look like maybe this is a third of the perimeter of the whole thing, it's not. It's exactly half. So I like to think of this as the one-dimensional ratio, because often you will only be given the side lengths of a full 2 or 3-dimensional object, and then we're going to have to do some stuff with that to find the proportions of, say, the areas of that same object. All right, so looking at this figure, and we could have this figure, but this one is, I like it more. This is split into 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles. And let's focus on this one here. Now, this point is exactly at the 1/3 mark of this whole side. So the proportion of the side lengths of this triangle, and thus the whole perimeter, to the side lengths of this triangle or the perimeter are exactly 1/3 as large as this one. So we can say the proportion of the larger to the smaller is 3 to 1. However, what if you're asked, what is the proportion of this smaller triangle's area to the whole area of the whole thing? It's obviously not 3 to 1. But if we knew that 3 to 1, we can find it. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles. So the proportion is 9 to 1. And we've gone up a dimension. We've gone from a 1-dimensional length, like a line, to a 2-dimensional area, right? And that two-dimensional area, in order to get that ratio from this one, we don't just have to count. You often won't be given a triangle to count the pieces out of. But if we were given the proportion of the perimeter or of a side length or anything, we can square it going from 1 to 2 to get that proportion. All right? And this also does apply to 3D space, and that's something that I'll touch on after a couple practice problems. Here is the definition of the ratios between similar figures. So if the ratio between the side length is r, you can also write ratios as, like, say this was there was a triangle and then another triangle, and the ratio was, this one was 3 to 2. If your ratio was 3 to 2, you could also write it like this, 3 to 2 or 3 to 2. I write it like this because it's more commonly, you know, it's a ratio and not a fraction. And this is very commonly how your problems will write it, if not the only way they'll write it. So I'm going to stick with this, but it could also look like this. And that would just be r. The ratio would be, in this case, like 1.5 to 1, because this is a fraction. This says that if the side lengths is r, then the perimeters are also r, so it's not more complicated than that, even if it seems like maybe this is a third to the whole thing. No, it's the same thing. And the ratio between the areas is r squared. Now, this one went from 3 to 1 to 9 to 1. This one would go from 3 to 2 in our first dimensional space to 9 to 4. So you do square both parts of the proportion, and that makes sense, because if we write it like this and we square it, we're going to end up with 9 over 4, not 9 over 2. So you do have to square both parts of your ratio. Cool? And this is 2D. All right. And then down here, this is just kind of a little fun fact. For a triangle, if you have all three angles of a triangle, I don't know why I did that before drawing the lines. What a weird choice. If you have all three angles of a triangle and all three angles of another triangle, and they are the same, you can say they are similar. Or if you have all of the side lengths of a triangle and all the side lengths of another triangle, you can say all the angles are the same. However, you cannot do the same thing for any other type of shape. Say you have a square, right? All the angles are 90 degrees. So it would be similar to another shape with all 90-degree angles, right? No, obviously not. You can draw a rectangle, and based on the angles, you have no idea if they're similar or not. They are not, because they have different proportions and side lengths. But for triangles, if they have the same three angles, they will always be similar. If they have all the same side lengths, they're going to be congruent, but, you know, that's not what we care about. Okay, this is not the kind of thing you'll have on your test, but it is a good starting point for seeing how the ratios work in math. And this is actually important in general, so try to figure this out, because it's very common on ACT and SAT stuff. If a yardstick, so 3 feet long, casts a 5.5 foot shadow, let's draw that. Pictures are going to be your best friend for a lot of this stuff. So 5.5 and 3. If a yardstick casts a 5.5 foot shadow, and at the same time a tree that it does not tell us the height of casts a 28 foot shadow, how tall is the tree? So we don't know. We're going to call it X. Now it says at the same time, so it's implying that this, the angle of the shadow is the same. So these are similar, is what it is implying. And we can set this up like this. We can set it up as 3 over 5.5 has to equal X, the corresponding side of the similar shape, over 28. I believe you can also set it up like 3 over the corresponding side has to equal 5.5 over its corresponding side. Yeah, you can definitely do that. You can do it either of these ways. I'm just going to go with this one for now, because the different parts of the same shape are on one side. And I find it easier. And also the X is on top, so we don't have to flip fractions or anything. So to solve this, we're just going to multiply both sides by 28 in order to find our X. And those will cancel out, and we'll get this. And I'll do this so that you can't see all the math I've done. And we have 28 times, or we can just do it like this, 28 times 3 over 5.5, 15.27 repeating. That is that x height. That's how tall the tree is, assuming that this angle is the same, which is implied. And that's how you use ratios. Now, the way we're going to use them is a little different, and honestly, I think a little, maybe not easier, but more the same throughout. So let's look at this one. Triangle J and F are similar. If the perimeter of J is 3 times the perimeter of F, so in the first dimension, J to F has the ratio, the proportions to each other of 3 to 1, because the perimeter is 3 times as big on J as to F. What is the ratio of the area of J to F? So just like that, just pure tutorial slide we did, all we have to do to get from 1D to 2D is square both of these, and that's going to give us 9 to 1. So your answer choice, well, there would be an answer choice that said 9 to 1, and you would choose that, and it's that easy. This is like basically a directly ripped question, so surely you can see that you can get some easy points here. In triangle ABC, AB equals 3 centimeters, BC equals 5 centimeters, AC equals 4 centimeters. I wrote at because finding the little angle sign was impossible in Word. I could have just copy pasted it from the resource, but whatever. Angle B equals 60 degrees and angle A equals 80 degrees. If in another triangle, EFD, EF is 10, FD is 6, and ED is 8, find the angle F. So what you have to do here is mostly intuitive. We're not actually going to do any multiplying or subtracting or dividing or calculus or anything funky. I'm just going to draw 2 triangles. And first we want to know if they're similar. So I'm going to do my A, B, C, and E, F, D. All right. And now I'll fill in these things that I know. So AB is 3, BC is 5, AC is 4. Now, obviously, this isn't proportional. It's almost close just because they're so similar to each other. It's so close. Shouldn't say that. Haha. But it's not really important. We just want to look at the numbers. Don't try. When you do your own sketches for this, there's too much to keep track of to get the proportions right. So just use the numbers. And we know that angle A is 80 degrees and angle B is 60 degrees. And we know the side lengths of this one. EF is 10, FD is 6, and ED is 8. Now it says find angle F. It does not explicitly state that these triangles are similar, but we can see that 6, 8, 10 are exact multiples of 3, 4, and 5, all by a factor of 2. And once you recognize that, so the proportion is 2 to 1 or 1 to 2 because the big one's over here. Once you recognize that, you can see that the angles are also going to be similar because the sides are. That's part of that triangle thing that I showed on the first tutorial slide. Don't worry about it too much, but we know the angles are similar. And if we line up our sides, so 6 is the corresponding side for 3. You can imagine they're kind of flipped along a mirror here, like whoop, because the 4 is still on the bottom. 6 is lined up to 3, so we're going to call that 6 base 1. Doesn't really matter. And then the 8 and the 4 we'll call 2. This is just so we can see the corresponding similar sides. Those numbers don't actually mean anything numerical. They're just for keeping order of things. And we're looking for angle F. So angle F is opposite the side that is 8 on this triangle. So it's going to be the same as the angle opposite the side that is 4, that same corresponding side on this one. So angle F is going to be 60 degrees. And we didn't do any math there. You just have to think about it. And really you have to draw it out. If you can do this in your head, fantastic. But you have a visual brain beyond my capacity. So probably draw little sketches. And a lot of the time on these questions, sketches will help. Some of them kind of require it. In the trapezoid PQRS, PQ is parallel to RS, so our bottom and top sides, they're the parallel ones on the trapezoid. And PQ equals 3RS. So PQ is 3 times as big as RS. I'm going to draw the PQ on the top and the RS on the bottom, much smaller, because we can, and you don't have to do that, but it's easier to understand what we're doing if you get the proportions somewhat close when you can see it. S, and usually you wrap around the letters here, and in a second you would know if you did it wrong. Because diagonals, PR, so if we did R right here, RS, you wouldn't be able to do a diagonal. So these diagonals go like this, PR and SQ intersect at O. O is usually the letter used for the center of something. Couldn't tell you why, but it is. Just get used to that. Fun fact, I guess. If the area of POQ is 72 centimeters squared, find the area of, oh, this is written weird, but whatever. Find the area of ROS. So this is POQ, that's this triangle, and ROS is this much smaller one down here. We're going to look for A, its area. And then it says POQ is similar to ROS. So these triangles are similar. But how do we know what their ratio is? Well, they told us that this side is 3 times as large. Well, I shouldn't write like that. But it's 3 times as big as this one. And we're looking at a triangle that is similar to this one. So its one-dimensional ratio is 3 to 1. We're looking at areas, though. So we have to square this to get up to our 2D ratio, which is 9 to 1. So we can set up, you could just like immediately see what you need to do here, but we're going to set up this ratio properly. So 9 over 1, that ratio needs to equal the ratio between these two areas as well. So 9 to 1, big over little, same as the big over little that the ratio is referring to. And then we can solve. It's pretty easy. We're going to flip both of the fractions first, which you can do 1 over 9 equals A over 72. And then we can multiply both sides by 72 to get 72 over 9 equals 8 equals A. So this area is 8. And you can see that the areas are always going to be a larger difference in proportion than the sides. So if you got something that was like kind of, if you accidentally used this same ratio, it would be pretty obviously wrong if the number wasn't like drastically different in proportion than what the side lengths were. All right. Now this is the ratio in 3-dimensional space. So say we have a cube. And this works pretty much the exact same way. The one thing you want to keep track of, I'll tell you in a sec. So this cube, we'll say, has side lengths of 1. All right? And then we're going to draw another cube that is similar, because all cubes are similar based on the definition. And this is going to have side lengths 2. All right? So the one-dimensional ratio here is referring to the edges, adding up all the edges, or just an individual one. And it's very obvious that this one-dimensional ratio is 2 to 1, just like we say right here. And then the 2-dimensional ratio is referring to the surface area or the area of one side, either or. Just like you can say one side length or the perimeter, and the proportion is the same between the two shapes, respective side lengths and perimeters. You can do the same thing with one side or the whole surface area. The whole surface areas of these have the same proportion relative to each other, the same ratio as one side to another side. And let's find them real quick. So one side of this 2 by 2 square is 4 units squared. And then one side of this is 1. So immediately we can see that one side is 4 to 1, just like this. But let's find the whole surface area just to prove that. So there are 6 sides. So this one is 6. And there's 6 sides here. So this is 24. So 24 to 6. And then you reduce that. You pretty much always reduce your ratios as far as you can. We reduce this and we will get 4 to 1 again. Pretty obviously. Now, you will notice that the next one is 8 to 1. And if that seems odd, that's fine. If that seems obvious, cool. It's just how it is. It shouldn't seem obvious or not, but good job, I guess, if it does. You do not use the 2-dimensional. I don't know why I erased those. Get to see me draw them again real quick. Woo! Those are cubes, I promise. And this one has side lengths of 2, and this has side lengths of 1. So the three-dimensional ratio, you don't do anything with the second dimensional. It's not 1 to 2, 2 to 3. It's 1 to 2 or 1 to 3. All right, so you're not multiplying by 2 to get this, and you're obviously not squaring it again or cubing it. To find the third dimensional ratio, you have to have the first, and you cube it. So just like you square to get to the second dimensional ratio, which is kind of intuitive, right? Because this will be given in units. This will be given units squared, and this is given in units cubed, volume is. So to find the three-dimensional ratio, you cube both sides of this ratio, and you'll get 8 to 1. And if we look here, this volume is going to be 1 times 1 times 1, so it's 1. And this will be 2 times 2 times 2 is 8. So 8 to 1. Even though this cube is only twice as tall as this one, it has 8 times as much volume. Which is, I might have mentioned in a previous video that watching those like graphs just rack up as side length increases is kind of nifty. It's really just a cubic function, but whatever. But yeah, that's that. That's the most simple one. And if you see, like if you had a couple shapes and their proportions were 7 to 8, right? 7 to 8. So very similar shaped cubes, whatever, similarly sized. It doesn't really matter what they are. Any similar three-dimensional shapes or two-dimensional, whatever. To get to the two-dimensional ratio, we square both of these, so we get 49 and 64. And then to find the three-dimensional one, we're going to get really big numbers. And they'll be further and further apart as you go. So we need to raise 7 and 8 to the third. So that's 343. And this is 512. So the three-dimensional ratio is 343 to 512. Which is, you know, it's a lot bigger, but it's important to know how to do this. There are two similar cones, J and K, and I'll draw them. It's not going to help us too much, but I'll draw them anyways. It's really not going to help us because I'm not going to redraw that. That's kind of what a cone looks like. That's a TP. I don't know. The circumference of the base of J, which we'll label them, is 8 pi. So this perimeter of the bottom is 8 pi, and the radius of the base of K is 8. So we want to find the proportion, the ratio between them. So let's go ahead and find just the radius of this to find our corresponding components of the shape. So if the circumference is 8 pi and circumference is 2r pi or diameter pi, whatever, then we know that r is going to be 4. 2r pi equals 8 pi. Solve that for 4. You know, shouldn't be too hard. So now we know our one-dimensional ratio is 2 to 1 K to J. And now it wants to know if the volume of J is 9. And we don't know the height, so we can't do the actual math for it. What is the volume of K? We can find our three-dimensional ratio by cubing both of these things, and it will be 8 to 1, just like that previous cube example. So if J, our smaller one, is 9, then our other one is going to be 8 times 9 because that's just the one. And the way you set that up in a ratio would be 1 to 8 equals, well, I don't know. It's easier to do 8 over 1 equals, no, it's not. Yeah, it is. Yes, it is. X, which is the volume of K, so I'll call it V actually, over 9. And we multiply both sides by 9. 9 times 8 is 72. 72 units cubed. All right, that's how you use, see, we didn't use the two-dimensional ratio at all because we just skipped right over it. We didn't need it. And that's how you use these ratios. And there should be one more. The ratio of the volumes of prisms P and Q, it doesn't tell us which type, doesn't tell us anything, really, is 343 to 2197. All right? So that is our third dimensional ratio. If a side length of prism Q is 65, what is the only knowable side length of prism P, assuming they are similar? So we need to get from our three-dimensional ratio, which is those big things, to our one-dimensional ratio. And we do that by cube rooting each of these things, just like we cube the one-dimensional one to get to here. So I think we just did this a little while ago. That's 7. So, oops, not square root. Make sure you use the right one. Control the caret. Cube root of 343 is 7. And then cube root of, what was it, 2197? Can I remember? Yes, is 13. So our one-dimensional ratio is 7 to 13. All right, so we will do this. 7 over 13 equals, and then we want our small over big. So we know that P is the small one, and Q is the big one because of the order that they're in. So this is going to be 65, and then our unknown side is going to be up here. So we'll multiply 65 times 7/13 to get 35 is the only knowable side length of prism P, because that's all the information that we have. And if we check that ratio, 65 over 35 should come out to the same as if we set up our proportion big over small. And it does. That's an easy way to check it. It should reduce every time to your original ratio, which I keep saying proportion. It's not the same thing. It's kind of the same thing. Live with it. Area of a circle. This whole quiz is pretty much just pi r squared, which is hilarious. I don't know why it's later. I assumed it wouldn't even be a thing, because you have to know this for the cylinder quiz and several other things anyways, but whatever. You need to know pi r squared is the area. You need to know that the diameter is 2 times the radius, which you had to know for the previous ones anyways, and that circumference is pi times diameter, or 2 pi r, which you had to know previously anyways. So you should be able to do this. What is the area of a circle with a radius 8? Taking pi is 22 over 7, because that's what they make you do. So pi r squared is 22 over 7 times 8 squared, which is 64. 201.143. That is literally pretty much a question on the test, about as easy as it gets. And this is units squared. Cool. A right triangle, PQR, has a right angle, that's supposed to be not like that, at Q, and is inscribed in a circle. I included this one. It's not even that terribly hard math, and you're going to have to take my word on something here, because I simply don't want to explain why it is what it is. But when something is inscribed in something else, I'm pretty sure, and that it applies here for sure, that means that all the vertices have to be touching the edge. Essentially, you're finding the largest shape that can fit into another one. So here, a right triangle might look like this. And because that hypotenuse is the largest side, and the largest chord or line across a circle you can make is the diameter, that hypotenuse is going to be the diameter. Just take my word for it. I'm not going to prove it. Sue me. It says that the right angle is at Q, and then P can be over here, and R can be over here. It doesn't really matter. It wants you to find the area of the circle knowing that PQ is 3 and QR is 4. So we can find the diameter with Pythagorean theorem. And it doesn't tell you that this is the diameter, but it's implied by the fact that it is inscribed. You're just going to have to trust me. So Pythagorean theorem, this is a 3, 4, 5 triangle. If you want to do Pythagorean theorem, go ahead, but this is a special one. 3, 4, 5, 5, 12, 13 or something. I don't know. There's a couple. And then we can split this in half to get 2.5 for our radius, and then plug that into the equation. So we're assuming it's 22 over 7 still, times that 2.5 squared. 19.64. This isn't terribly hard math, but it is kind of confusing, especially if you didn't know what it meant by inscribed in there. The circumference of two circles are in the ratio 4 to 5. Find the ratio of their areas. So you do need to understand the previous quiz in order to do this question, which is a weird way of writing these quizzes, but whatever. Should just focus on the one thing. Because you could also do this with some methods that we used previously, or just like raw algebra, but now we know this trick, essentially. So if the circumference, which is a 1D thing, right, it's a perimeter, is in the ratio 4 to 5, and the area is a 2D ratio, and then all we have to do is square both of these things. So the ratio is 16 to 25, and that would be your answer. That would be as far as it goes. You don't have to do any fancy math for this, right? Which is nice. I included this one as well, just so you knew how to do this. So a bicycle wheel makes 3,000 revolutions in moving 9 kilometers. What that means is that the circumference was completely traversed 3,000 times over 9 kilometers. So to find the circumference, we divide 9 kilometers, which will change into meters here. So 9,000 meters, just to make our lives easier. The answer choices will either be in meters or centimeters, most likely. And we're going to divide it by 3,000 times. So the circumference is going to be 3 meters. Right? So that's the circumference. We want the diameter. If the circumference is the diameter times pi, then we have to divide out the pi from this 3. So 3 times 7 over 22, which is the same as dividing by 22 over 7, is going to give us, let me just control enter from the get-go, it's going to give us 0.9545 repeating. So this is 0.9545 repeating meters. Or if it was in centimeters, your answer, it would be 95.45 centimeters. And it probably would be, just because they don't like doing this thing all the time. I believe that's all I have for the area of a circle. That's, they can only make that so complicated. Now we get to look at 3 different properties of angles when you throw lines onto a circle. And these aren't explicitly difficult, but you have to keep them memorized. So there's kind of a bit to do. I don't want you to look at this yet. I want you to look at this. Central angle is what we usually think of as an angle in a circle. And all it is kind of, it's the same as an arc angle. And the arc angle is just kind of an expanded version of a central angle. So if the central angle is, like 100 degrees, then so is this arc angle that is created by the endpoints of the lines making this angle. Same thing. Now, an inscribed angle is when you have a little angle, a little vertex on one side of the circle, and it extends all the way to form an arc angle, and we don't have any center angle to look at for this. It goes all the way out far enough to have an arc angle as well, these 2 lines. And every single time, and you're welcome to read the resource and figure out why, it's just a ton of algebra for the proof, but if you're interested, go ahead. The inscribed angle connected to an arc angle is always exactly half as big as the arc angle. And we can see that this is pretty big, right? Like if we put a dot in the circle, that's a much fatter angle than that. And it's exactly twice as fat. So if this angle is x, then this angle is 2x. And if this angle is z, this angle is z over 2. An inscribed angle whose ray passes through the center of a circle. Oh, actually, ignore this. This is the pre-proved version. I just included it so that you could see that's only, it's saying that it only counts if it goes through the middle of the circle, but it works for any of them. Any inscribed angle is half as much as the arc angle it is attached to. So, looking at this problem, if POQ, so this angle, and O is the center of the circle, is 130. And here's a hint. That center angle is the same as the arc angle caused by these two endpoints. So this arc angle is also 130. Find the measure of PRQ. So that makes it so that this is an inscribed angle for this arc angle, which is 130, because the center angle is the same as an arc angle. And we know that this is going to be half as big as that. So all we have to do is divide 130 by 2 and get 65 degrees. Not particularly hard. By the way, these are ripped straight from the test, and I changed the numbers. I did not have time to... I didn't have time to draw a ton of these problems. This takes so long. So all these pictures, except for this one, actually. I did do this one. But this is not actually a problem. All right. A chord is a line between 2 points on a circle. So it doesn't have to go through the center. It's just a line that ends on the edge of the circle. The diameter is the largest chord you can make. Just a fun fact, really. When two chords intersect in a circle, the angle between them, so theta here, is equal to the average of the arc angles formed by the two chords. So this angle equals the average of here, A and B. So A plus B over 2. And this is the same thing. These are vertical angles, I was recently informed. So these vertical angles are the same. If you were given some C and D here in degrees, then this angle, which we can call Z, it doesn't matter, would equal C plus D over 2. It's just the average. So inscribed angles are double in arc length. The angle in the middle of two chords is exactly the average of the two arc lengths. And we'll do this problem here with that. So AEC is 50 degrees. These are all degrees. I just had to block out the other numbers. 50 degrees right here. CB is 90 degrees. And BFD is 70 degrees. What is the measure of AOC? So that is AOC, this angle. Also a congresswoman. So this is the angle formed by two chords, and we have these two other arc angles, arc lengths, arc whatever, attached to it. So we actually don't need to look at 90 at all. It's just there to trip us up. And the average of these two things, we add them together to get 120 over 2 is 60 degrees. So the measure of angle AOC is 60 degrees. Right? That's the simplest way this can go down, but I'm really only going to do the simplest way these can happen, because to show you anything more is basically just doing the test for you. And you can figure it out for the most part if you really understand these properties. And they often are intertwined. So just understand all of them. Those lines are called secants. A secant is a line that starts outside of the circle and then ends somewhere on the circle after it goes through it. Don't look too deeply into the fact that that's the same word as some other math stuff. I'm sure it's related. I don't care how. When two secants intersect outside a circle, so like this, outside the circle, the angle between them is half the difference between the angles of the intercepted arcs. So the arc lengths formed by those secants. Not the outside ones, the inside the secant ones. So we added together two arc lengths and divided by 2 to get the average previously. For this one, we're going to subtract the smaller from the smaller and divide by 2 to get this one way out here. And you can see that this is smaller than this is than this. Like this would be a very large angle. This would be a slightly less large angle, and that's the smallest one of all. So as it goes, it gets bigger. So this is going to be pretty small. If the measure of the arc QS, so this here, is 30 degrees, and the measure of arc RT is 154 degrees, find the measure of QPS, which is this right here. So we're going to subtract the smaller from the bigger and divide by 2. And we will get this angle here. I think it's whatever. I'm going to do it like this. Could I do that in my head? Maybe. Who cares? 62 degrees. is how big that angle is. And that's how you use that property. I think I included one more, just so you can see how secants are not always given to you pretty like this. Sometimes they're implied. So if we look, a quadrilateral PQRS is inscribed in a circle. The measure of arc PQ, so this here, is 110, and the measure of the arc RS is 50. Find the measure of the angle between sides PS and QR if they are extended until they connect. So you might read that and be like, but all it is that these are really long secant lines now. Like really long. And where they meet up is an angle that will use that same property we just used to figure out. So 110, the bigger, minus 50, the smaller, over 2 is going to equal this angle theta way over here. And this one, surely, I'm so tired, surely I can do some head. 60 over 2 is 30. Right? Yeah. 30 degrees. And that's how you find that one. That's all I have for you. I think this is actually a pretty long video, even though I didn't go into any really complicated problems, just because there's a lot of concepts to go over. I don't think any of them are too hard. Just study them, memorize them, breathe, eat, sleep them, and you'll be fine. Good luck!